Most people assume metal technology simply improves over time, that what we make today must be better than what was forged 80 years ago. But when you walk through abandoned shipyards, forgotten rail depots, or coastal gun emplacements from the Second World War, something unsettling becomes obvious. Much of that steel is still structurally sound, not pristine, but intact, stable, and stubbornly resistant to the kind of rapid corrosion that destroys modern vehicles, appliances, and infrastructure in a fraction of the time. This isn't nostalgia, and it isn't survivorship bias alone. There are real material, industrial, and strategic reasons why so much pre-era steel endured. Understanding those reasons reveals something deeper than metallurgy. It exposes how wartime necessity reshaped manufacturing priorities, and how modern efficiency quietly traded away forms of durability most people never realized they were losing. If you value serious historical analysis that connects past decisions to present realities, subscribe to The Survival Record now, and stay with this one carefully, because the steel itself tells a story about preparedness, industrial philosophy, and what societies choose to preserve when survival is the priority. Organizations like the British Admiralty enforced rigorous anti-corrosion procedures, particularly for maritime equipment. Even when maintenance became irregular late in the war, the original protective systems were robust enough to delay deterioration for decades. Modern coatings prioritize environmental compliance, cost control, and ease of application. They are safer, but not always as long-lasting. The urgency of survival eliminated economic incentives to underbuild. Peacetime manufacturing operates under competitive pressure. Materials are minimized, lifespans are calculated, replacement cycles are expected. Wartime production followed a different logic. Factories did not design for consumer turnover. They designed for operational survival under uncertainty. Equipment might be deployed in tropical humidity, Arctic cold, saltwater exposure, or extended storage with limited inspection. Over-engineering was often the safest assumption. Steel infrastructure, built in industrial centers such as Pittsburgh, reflected this mindset. Production targets were immense, but structural failure inside manufacturing facilities could halt weapons output entirely. That risk justified conservative engineering margins that modern cost analysis would rarely permit. In survival terms, redundancy was cheaper than interruption. Not all wartime steel performed perfectly, and that also shaped what survived. The historical record is more complex than the myth suggests. Certain World War II steels suffered catastrophic brittleness, particularly in cold environments. Some Liberty ships famously fractured due to metallurgical and design limitations, combined with welding practices still being refined under extreme production pressure. But here is the critical point. Materials that failed quickly were replaced, repaired, or scrapped. What remains today disproportionately represents what endured best. This selective survival creates the impression of universal superiority. In reality, wartime steel production involved enormous experimentation under pressure. The examples still standing are often those that benefited from conservative design, favorable environmental exposure, or effective protective treatment. The durability we observe is partly engineering and partly historical filtering. Maintenance culture during wartime treated corrosion as a strategic threat. Corrosion was not merely a maintenance issue, it was a readiness issue. Naval doctrine recognized rust as an operational hazard, capable of disabling weapon systems, weakening hull integrity, and compromising mobility. Maintenance crews were trained to treat corrosion control as continuous preventive action rather than periodic repair. This mindset influenced long-term durability even after equipment left active service. Structures built under systems designed for constant preservation began life with unusually high protective standards. Modern civilian infrastructure often assumes predictable inspection schedules and component replacement. Wartime infrastructure assumed disruption and prepared accordingly. Industrial fuel sources also influence steel's long-term behavior. The chemical composition of steel depends partly on how it is smelted. World War II-era blast furnaces commonly use specific coal and coke sources with distinct impurity profiles. Trace elements such as phosphorus and silicon varied by region and ore type. These variations could produce steels that weathered differently depending on environment. Some developed stable oxide layers that slowed further corrosion, a behavior later intentionally engineered into weathering steels like CR10. Wartime metallurgy did not fully understand all these long-term effects, but certain combinations of ore, fuel, and processing conditions inadvertently produced steel that aged favorably in open-air exposure. Industrial geography became part of the material's survival characteristics. What this reveals about modern manufacturing priorities. The comparison between World War II steel and modern steel is not simply technological, it is philosophical. Wartime industry prioritized resilience under uncertainty. Modern industry prioritizes efficiency under predictability. Today's materials are often optimized for performance-to-cost ratio, weight reduction, recyclability, and controlled service life. These goals are rational within stable supply chains and maintenance systems, but they produce structures that assume continuity. Wartime structures assume disruption and were built to endure neglect, damage, and delay. For survival-minded observers, that distinction is not academic. It reflects two fundamentally different approaches to risk. The deeper lesson is not about steel, but about preparedness. The persistence of World War II steel is a physical reminder of how societies behave when failure is unacceptable. Industrial systems became conservative. Materials were abundant relative to uncertainty. Protective measures were layered. Maintenance was continuous. Design margins were generous because the cost of collapse exceeded the cost of excess. These are not uniquely military principles, they are survival principles applied at national scale. When modern observers notice that old steel seems to last longer, what they are often sensing is not lost metallurgical knowledge, but a vanished tolerance for overbuilding. Durability was not accidental, it was policy. Understanding why World War II steel still stands forces us to confront how material choices reflect strategic priorities. It reminds us that resilience is rarely the most efficient option, but it is often the most enduring one. And when we study the physical remains of that era, we are not just examining metal, we are examining decisions made under the pressure of existential risk. If careful historical analysis like this matters to you, if you believe material history still has lessons for preparedness today, subscribe to the Survival Record and share this video with others who value depth over simplification. Because sometimes the most revealing artifacts of war are not weapons or battlefields, but the materials that quietly refuse to fail.